In this tutorial you will learn how to design a PCB in the LibrePCB board editor, how to run the design rule check and how to order the PCB either directly or through generating production data. This tutorial assumes that you already have drawn the complete schematics of your PCB in the schematic editor. If you didn't create the schematics yet, please check out the corresponding tutorial video first. Once your schematics is complete and all ERC issues are resolved, open the board editor to start with the PCB design. The first thing you should do is to specify some settings in the board setup dialog. As always, you could adjust these settings at any time later, but some settings might cause additional effort when changing them during the design phase. The name of the board is not that relevant, especially for typical projects containing only one board. So you can just keep the default name. The number of inner copper layers on the other hand is very important, of course. Top and bottom copper layers are always added anyway, so a value of 0 creates a 2-layer board, and a value of 2 creates a 4-layer board. Typically the layer count should be a multiple of 2. The following settings specify the appearance of the board, affecting mainly the 3D viewer and the production data export. The most relevant setting here is what objects you like to put on the silk screen or not. By default the legend drawings and component names like R2 are shown on the silk screen, but values like 10 kilo ohms are not shown. You could enable more or less silk screen content depending on the density of your design. On the second tab you can configure the behavior of dynamic board objects. For example, the stop mask expansion of pads is usually calculated from the pad size automatically according the rules defined here. Or whether vias are covered with solder resist or not is determined by comparing their diameter with the value specified here. For more information about particular settings, check out the tooltip shown on mouse hover. Note that unless you have special requirements, all the default values are perfectly fine, so most of the time you don't need to worry about them. The last tab allows to configure the settings of the design rule check, or DRC, which helps you to find issues in the layout. In contrast to the design rules we discussed before, DRC settings have no impact on the layout at all. They only impact what messages will be emitted by the DRC. For accurate messages, these values need to be gathered from the PCB manufacturer you intend to order the PCBs from. Many PCB manufacturers list their capabilities on their website, at least the most important values like the minimum copper clearance and width. If you are not familiar with this task, don't worry too much about it. With the default values you should always be on the safe side and they are good enough for rather simple designs. Typically they only need to be adjusted for more complex designs. If you already know the desired size of your board, it's a good time to specify the board outline now. Every board is automatically initialized with a default board outline polygon, so you only need to move its vertices according your needs. To insert exact coordinates, double-click the polygon. Arcs can be added by specifying the arc angle on particular polygon segments. If you prefer to draw the board outline from scratch, just draw a closed polygon with a line width of 0 on the board outlines layer. If you need mounting holes, use the Add Hole tool. This creates non-plated circular holes or slots. Here again, exact coordinates and other properties can be entered with a double click on them. Arbitrary non-plated cutouts can be added with the Draw Polygon tool. Just make sure to select the board cutouts layer, a line width of 0, and draw a fully closed polygon. Please note that such cutouts should always have rounded corners since sharp corners as drawn here cannot be manufactured by a milling tool. Currently these rounded corners need to be added manually in the Polygon Properties dialog. To quickly see if everything looks good, just open the 3D viewer. If the preview doesn't look as expected, check if all polygons are on the correct layer and are exactly closed. If desired, you could lock the placement of these objects now. This avoids accidentally modifying these objects by dragging. Now we have to add all the components from the schematic to the board. Open the Place Devices panel to see the unplaced components. Select the next component to add, in arbitrary order. Then we have to decide for a package we like to add by choosing a device. Remember that for some components we have already chosen the device in the schematic editor, but not for all of them. If we have already chosen a device, it will be automatically selected here and a check mark is shown next to it. If we didn't choose a device in the schematic editor, no check mark is shown and we have to select it now. In this case, please don't just take the default selection since it might not be what you want. Note that some packages also allow to choose between different footprints, but this selection is less critical. Sometimes you can choose between different mounting variants, sometimes between hand soldering and reflow soldering footprints. So if you intend to manually solder the PCB by a soldering iron, you could choose a footprint with larger pads to make soldering easier. Now you could add all identical components at once? Or one by one, which is the recommended way since it enforces you to review each component individually. While a device is attached to the cursor, press the R key to rotate it or the F key to flip it to the bottom board side. A left click finishes the placement. Repeat these steps for all the listed components. For a more fine granular placement, adjust the grid interval accordingly. To see the recommended clearance around devices, enable the package outlines and courtyard layers. Generally, the courtyard polygons should not overlap with the package outline polygons to make sure the PCB can be assembled without problems. Unfortunately, we can't give you any recommendation where to place the devices since this is individual for every project and is a matter of experience. However, generally you should always keep an eye on the yellow air wires and try to find a device placement which minimizes the number, length and interceptions of air wires, as this will make layouting the copper traces easier. Note that it's also possible to automatically add all devices at once. But unless you specified all devices in the schematic editor, this is not recommended since the automatically chosen devices may not be what you're looking for. However, devices and footprints can still be changed at any time through the context menu. Just as already done for the board outline, the placement of devices can be locked as well. For example, if the position of a connector is critical, just lock it to avoid moving it by accident during the further design process. Once you placed all devices at least roughly, it's always a good idea to check if everything looks good so far. The first thing you can do is to run the design rule check, also called DRC. If the device placement violates any copper clearance or courtyard clearance rule, you can fix the issues right now before adding any traces. Note that since we didn't add any traces yet, the missing connection errors can be ignored for now. The second thing which you should do is to open the 3D viewer. Here you'll get a good impression how the final PCB will look, and many potential issues would be visible here. For example, is there enough space around holes to insert screws? Are all pads accessible by a soldering iron? Is there enough space around connectors for their mating part plus cable? Here you'll also see the text labels on the silk screen as configured previously in the board setup dialog. Just move text labels around to avoid overlaps. As already known from the schematic editor, these labels can also be removed or restored through the context menu. In contrast to name labels, value labels are not put on silk screen by default, but they are still useful if you like to create an assembly plan containing them. If you don't need values at all, feel free to just delete them. If you like to have some of them on silk screen and some not, you could just move them to a different layer. By the way, you might remember that adding a device to the board copies the corresponding library elements from your workspace into the project. so any further modification in the workspace won't propagate into the project. If you modify, for example, a package already added to the project, you need to manually trigger an update in the project to receive these modifications. Just open the Project Library Updater and click on the Update button. Note that this will update all library elements used in the project, including symbols, footprints, and more. Also be aware that if the position of pins or pads have changed in the workspace, the update could slightly mess up some wires or traces in your project. Now it's time to add the actual copper traces to make the connections as specified in the schematics. Each connection is indicated by air wires, so basically we have to replace all air wires by copper traces. In the Draw Trace tool you can choose on which layer to add the next trace, its width and the dimension of vias to connect traces across multiple copper layers. Of course these properties all heavily depend on the exact use case, so we can't make any recommendation here. However, for general-purpose projects without special things like high currents, the default values should be fine. As already known from the schematic editor, start a trace by clicking on a pad, use the right mouse button to switch between different routing modes, and add more vertices with the left mouse button. A trace is automatically finished when ending at a pad or within another trace. Note that the cursor automatically snaps to footprint pads and trace vertices to support making connections outside the grid interval. If this is not desired, hold the Shift key to disable snapping. Although the layer can be selected in the toolbar, LibrePCB automatically switches to a different layer when starting a new trace at an already existing trace or pad. This can be avoided by hiding the other copper layers. To quickly move a device, the tool can be exited with a right-click on the background. Afterwards, press the right mouse button again to switch back to the Draw Wire tool. Just make sure there's no object below the cursor, as this would open the context menu. To place a via, just change to a different copper layer while drawing a trace, either in the toolbar or with the page up and down keys. This will automatically insert a via with the specified properties. Standalone vias, like stitching vias, can be added with the dedicated Add Via tool. Whenever you're unsure if there's enough clearance between traces or pads, you can trigger a quick check. This is basically the DRC but runs only the most important checks to get much faster feedback. Mainly copper widths and clearances are checked, so this tool is especially handy while drawing traces. Copper planes, or sometimes called copper pores, can be added to fill an area with copper of a particular net. A typical use case is to add a ground plane and maybe also a plane for the supply voltage. They are useful for shielding reasons, to create low impedance connections, or just to simplify connecting many pads. In fact, planes can be used instead of traces to connect pads with each other. To add such a plane, select the Add Plane tool and choose the net and the copper layer of the new plane. Then draw the outline with the left mouse button. A double-click or escape finishes the drawing. Since planes are automatically clipped to the board outline, a very rough outline is good enough to fill the whole PCB. Note that each plane is located on a single layer, so if you need a plane on several layers you have to add a separate plane on each layer. This can be done by copy and paste and changing the layer afterwards in the Plane Properties dialog. It's also possible to add an island of another net within a plane. Just make sure to configure a higher priority than the outer plane to avoid relying on the default drawing order. Please also note that planes are only filled if there is any pad, via, or trace of the same net located within the plane. To exclude a particular region from the plane, draw a keep-out zone on the corresponding layer and make sure the No Planes option is checked. As quickly mentioned in the previous tutorial video, LibrePCB allows to create multiple boards within a single project. This is a rather advanced topic and generally you don't need to know how this works, so feel free to skip this chapter. However, in some situations this feature can be handy, so we will quickly take a look at that. Basically, this feature is intended for two different use cases. The first one is to fork a board during the design phase to try out a different placement or routing strategy. For example, if you struggle in the middle of the design phase whether the device placement was a good idea or not, just duplicate the whole board, revert the things you're not happy with and continue with a different placement. Or if you are unsure whether you need 4 layers or only 2 layers, you can duplicate the board and continue with a different layer count. Then you can decide at any time later which of the approaches is the best and just delete all the other boards. The second use case is to actually create different boards for the same circuit, for example to create a board in different form factors. Or a through-hole prototype board with test points, and a surface mount high-density production board. The workflow is exactly the same, you just keep several boards in the project and generate production data for all of them. As explained in the previous video, all boards are always in sync with the schematics. For example, if you delete a component in the schematic, it will immediately disappear from all boards. Also note that the assembly data of components is a bit more complicated when added in different packages to different boards. In this case, you'll see all the corresponding devices listed in the Component Properties dialog and each manufacturer part number is valid only for a particular device. At the end of the board design phase, you should review it in several ways to make sure it doesn't contain any mistakes. The most important thing is to run the design rule check as it detects any short circuits, too small clearances and many more. Just click on a message to highlight the problem in the board editor. Note that fixed problems do not disappear automatically from the list, you always need to trigger the DRC again after making modifications. DRC messages can also be approved if you're sure a particular message is not relevant. Another good idea is to review the board manually in the 3D viewer since all the relevant layers are visible here. Copper layers, solder resist, silkscreen, and even the solder paste which gets applied through the stencil. Each of those layers can also be reviewed in more detail by enabling only the corresponding layers. Beside the predefined layer groups, you can toggle each layer individually, for example, to review only the stop mask or a particular copper layer. You may also use the measure tool to check certain distances or board dimensions. If you like to generate a bill of materials, you should also review its content to see if there is some incomplete assembly data for particular components. Once your board is finished, there are two different ways how you can produce the PCB. The traditional, but more complicated way of manually generating production data will be explained in the next chapter. This chapter explains how to directly order the PCB through the integrated fabrication service called LibrePCB Fab. This way is easier, faster and less error-prone than the traditional way. You are just limited to the PCB manufacturers supported by LibrePCB Fab. Especially for rather simple projects and for beginners in general, using this service is highly recommended since it avoids many potential pitfalls. To do so, just click on the Order PCB tool button and start the order process with a click on the Upload button. This will open your web browser to proceed the order process. Here you may quickly review the electrical rule check messages, the number of copper layers and the board dimensions. Then select the manufacturer where you want to place the order. Currently we support Eisler and PCBWay. Generally we recommend Eisler because of its very simple and foolproof order process. They even perform further analysis on your board and let you know any found issues before placing the order. PCBWay on the other hand provides more capabilities but its order process is less guided and less automated. The Continue button now redirects to the website of the chosen manufacturer where you can specify some order details and place the final order. Since the further order process depends on the chosen manufacturer, please check out their documentation for more information. Generally, the most important options are the number of PCBs to order and whether you also like to order a stencil for soldering surface mount devices. The further order process will then ask for the shipping address and payment information. As this is all self-explaining, we'll abort the order process now by just closing the web browser. The other way to order the PCB is to generate Gerber files and send them to manufacturers manually, which is the traditional way. Gerber files are also needed if you plan to etch the PCB by yourself. In addition to Gerber files, this chapter also explains how to generate other production data. Generally there are dedicated dialogues to generate Gerber files, pick and place files, netlists and so on. However, these are considered as legacy and will probably be removed in a later release. The new and recommended way to generate any production data is by adding output jobs as we already saw in the schematic editor tutorial. Just like the schematic PDF output job, an additional output job needs to be added to generate Gerber files for PCB production. Note that currently there are two presets available which represent exactly the same job, just with different initial settings. This is where the difficulties start. Since naming of Gerber files is not standardized, you need to check our manufacturer's documentation to choose the correct settings. Our first preset uses settings which we consider as most reasonable. But especially cheap PCB manufacturers are often not able to handle them correctly, thus the second preset is optimized for those cheap manufacturers. However, we cannot give any guarantee that they work correctly with any manufacturer. Please also check out our documentation about all the available configuration options. Note that by default, only the first board gets exported. If you have multiple boards in the project, choose all boards and make sure the board name is contained in the output file path to avoid conflicting output files. Exactly the same procedure also applies to generating other output files. For example, comma-separated pick and place files, bill of materials, or an assembly plan as a PDF. If you like to bundle several output files in a zip, for example to send them to the PCB manufacturer, add an archive output job and choose the output files to be added to this zip archive. Creating an archive of the whole project might also be useful since this allows to open the current project revision from your file manager at any time later. To actually generate the output files, run the corresponding jobs or all at once. This will write all files into the output folder of the project. Note that if there are any unknown files in the output folder, LibrePCB reports them when running a job. If desired, those files can be deleted with the Clean button. At the end, don't forget to click on the OK button to save the new output jobs. Attention! If you continue working on the project after a PCB has been ordered, it's highly recommended to bump the version number of the project. This avoids overwriting the just generated output files by accident when generating the output of the next revision. Keeping all output files of each PCB revision is always a good idea for documentation purposes.